All right, so when we did our notes on 4-4, the very last question said find the area of the region bounded by the graphs of the equations, and they gave you more than one equation so that you could make sides with those equations to bound in a region. So we're going to look at question number 41 out of the book, just as a sample to remind you of what we discussed. And then you'll have a few like this for homework. So the original equation is y equals x to the third plus x. And the two secondary equation type thoughts to help bind it is x equals 2 and y equals 0. So the first thing you'd want to do is graph the equation that's more complicated looking, because that's the main equation. And it doesn't tell you what x to start on and what x to end on, but it did give you an x kind of that's in that range, and then it gave you a y value. Those are vertical and horizontal lines. So they're easy to put into your graph because y equals 0 is this line. And x equals 2 is a vertical line over here. So I just got to put this one in to see, kind of where does it cross those. So if you just plug a few numbers in and start trying some, if you plug in 0, you get 0. So I already have touched the y equals 0 line. If you put in 1, you get 1 cubed plus 1 equals 2. And if you put in 2, which is the other vertical line, is going to be cutting it off on that side. 2 cubed plus 2 is going to be 10, which is going to be way up here. So there's my bounded region. Y equals 0 bounds the bottom. X equals 2 bounds the right side, and the curve itself bounds the left side. And I don't know what the rest of that curve looks like, which I could put in, but I don't have to put all of that in if I'm doing it by hand. Now, if I put it in the calculator, I could draw the whole entire curve in there. But I don't want to take time to draw all that when I'm just wanting to find that bounded region. Now, the question after you draw the graph says integrate from what x to what x. So what x did I start on? What x did I end on? That's right, 0 to 2. And then you put your more complicated formula in that was not a vertical and horizontal line with dx. And then you integrate. So that's going to be 1/4 x to the 4th, because if I add 1 to the power, that's going to put a 4 on the bottom, but I'll bring it out. And that's going to be x squared. Put a 2 on the bottom, puts a half in front. Evaluate from 0 to 2. So first I got to put 2 in both of them, and then I got to put 0 in both of them. Now 0 is pretty obvious. What's 0 going to do? Yeah. So basically I really just got to work out what 2 does and say subtract 0. So I remind myself that I did physically plug 0 in, but it don't make anything, so I won't write it down. So 2 to the 4th is 16, and divided by 4 is 4, and 2 to the 2nd is 4, and divided by 2 is 2, so 2 plus 4 is 6. So you're just integrating the problem, but the information helps you to figure out what x to start on, what x to end on. And that's what the graph's there for. What do y'all think? Pretty simple? Not bad. Now, you can use your calculator to help you graph as much as you need to, or make a table of values. But the key is if you put that vertical and horizontal line in there, then that helps to break it all up a little bit so that you can kind of see where you got to cross both of them. Now, the next thing is, how do you find the second fundamental theorem of calculus? The second fundamental theorem of calculus is about taking a problem and integrating and differentiating and seeing what it goes back to. So the rule says that if you differentiate with respect to x, an integration problem that has a number at the bottom but a letter x at the top of f of t dt, which makes no sense that I'm differentiating kind of with respect to x if there's t's in there. But if I integrate it, the x will be in there, right? That the answer to this question kind of looks like all I did was put x in place of t. Now, yeah, no. So be careful. Because differentiating something and integrating something are opposite operations of each other. But there's a little bit more to it than that. And that's why it's a little deceiving. But it looks like all I did was put that x right there and that's the answer. Does that really look like that to y'all? Okay. It's almost that. It's just a little bit more complicated than that.
So is that x over a or 4 0?
It's an x and an a.
Okay. So
Yeah.
it's a 4 0.
All right. Now, a can be any number, and whatever number that is makes absolutely no difference in the answer. What does make a difference is what's up there at the top. What kind of letters you have. You know, a variety of different things can be put up there. It don't have to just be an x. But to show you why this comes out the way it does, we're going to look at one question the long way. So our original problem, capital F of x, is going to be equal to this integration problem. And we're going to integrate it, and then we're going to go back and differentiate it to see what does it go back to. So when we integrate this problem, would everybody agree this is going to become t squared with a half in front plus 2t. And we're going to evaluate it from 0 to x. So when we evaluate that from 0 to x, that's going to put x's in for the t's, right? Minus 0. Everybody agree with that? Okay. So capital F of x is going to be equal to 1/2 x squared plus 2x minus 0, but we're going to throw the minus 0 away. So that's why this stays that way. Because if I put 0 in, it's not going to do anything. And even if I had a number to put in there, it wouldn't matter. So let's just say, for instance, that I had 5 down there, and I plugged 5 in both of these and got an answer. It's not going to make any difference. Here's why. The next thing you do is you go back and differentiate it. And what happens when you differentiate a number over here? It goes to 0 anyway, doesn't it? Think about it. If I had a 5 over here, wouldn't that be 0? If I had a negative 21 over here, wouldn't the derivative be 0? So it doesn't matter what number is down here for a. Mine happens to be 0, but it doesn't have to be 0 because it would go away when I differentiate. So now when I put the 2 in front, that becomes x. And when I take the derivative of this constant, it becomes plus 2. And if you look at it, based on the original question, doesn't it look like all I did was just put an x in? Okay. Now that's a little deceiving, but it is very much like that. And here's why it's a little bit deceiving. Because it told me to integrate this, and then I'm supposed to be differentiating it with respect to x. And what's the derivative of x? 1. And that's why it's that easy. But not always is that x up there at the top. And if it's not x, it does affect the problem. Now, but is it?
If it's from 0 to x, we just can fill in the x.
That's what the second fundamental theorem of calculus says.
That's it.
Mm-hmm.
Man, you should let me make some up here.
All right, now what we're going to do is we're going to look at another example and show the short way of writing it, so that you can see it can be a lot shorter. But then we're also going to look at a couple of examples in which the top's not x, or maybe not even the bottom is x. Come on, board. What's wrong with you? There we go. All right, so differentiate with respect to x. Uh-huh. All right. So the second fundamental theorem of calculus basically states that if you need to integrate and differentiate a question, and why this works, y'all, the way it works is because when you integrate and you differentiate, this is the differentiation. When you write an integration problem, this piece inside, the square root of t, is the differentiated answer for some function that we don't know. So when we were back over on the other page, and we had this 1/2 t squared plus 2t, what I'm saying is the differentiation of that is t plus 2. So that's why if you differentiate and you integrate in the same question, it goes back to the original problem, because you've undone it. But that is only true if the derivative of this piece at the top is 1. That's right. In this case, I'm just replacing the t with an x, and I get the square root of x. Oh, excuse me, cube root. Thank you. I forgot it was cubed. Yeah, it's not. No, sorry, y'all. Cube root of x. I forgot it was cubed. All right, now, what if you look at a question, though, and the top's not an x? Yep. You do, but there's a little extra work you have to do. So let's look at that. And not always are the questions written in this format. So I'm going to write this one in a different format to show you. So a lot of times they'll just say capital F of x is equal to. And this is 2x cubed sine of t squared dt. All right, so for starting off with, it kind of is like that, okay? If someone gives you a function like this and says integrate it and find me capital F of the x dx, then they're saying differentiate this with respect to x. And when they tell you to differentiate with respect to x, this notation right here can remind you of something where this notation does not. So that's why I'm writing this. I'm going to show you what it reminds you of. All right. So now that I've got my differentiation set up with my integration problem, we know, based on what we studied so far, that this x cubed is going to come in here and replace this t. Everybody agree? That's what we've learned so far. To take that x cubed in there and replace it for the t. And sometimes you might need to simplify a little bit. But what you have to understand is this means differentiate that x. You see, when we did the others, they were all differentiations of x, and x is 1. So it didn't show. But this piece right here is telling me I need to take the differentiation of that particular term because it's not 1. It's 3x squared. And multiply it out here in front. It's kind of like chain rule. Second fundamental theorem calculus is kind of like chain rule. You plug whatever's up there in, but if the differentiation of that is not 1, you got to multiply by it. And that's all you got to do. Now, I probably should change this to x to the 6. But other than that, that's it. That's about all you do.
So you multiply, sorry, go ahead.
So we move the x cubed where the t is at,
Hmm.
and we differentiate it from.
Exactly.
You see?
It's like chain rule.
So you keep,
So my sine of 6 to the x is what I get from plugging in x cubed there. But this part out here in front is the differentiation of the power. And that's why the first two examples don't show that, because the differentiation of x is 1. So it kind of gives you a false sense that you're always just going to be plugging it in, but it's not really that you're just plugging it in. All right, let's look at one more. All right, so this time we're going to do it from x to x plus 2. So there's a problem. We got x's on both ends. And 4t plus 1 is what we're integrating dt. Now, this fundamental theorem of calculus that we're looking at here for the second fundamental theorem only works if there's a number at the bottom. So if there's not a number at the bottom, we need to revamp our question a little bit. So the idea is we break it into two problems. And you pick a number, and it don't matter what number you put. It absolutely does not matter what number you put. So I always just put 0 because it's just easier. So from x to 0 is one of my problems. And from 0 to x plus 2 is my other problem. Now, before we go any further, what's the derivative of x? And what's the derivative of x plus 2? 1. Those are not going to affect my final answer to have any extra stuff put in front of it. Does everybody see that? But this one's backwards. Yep, we got to take a negative out. So that means if I want to turn that around, I take a negative and put it in front of the integration. And then I'm ready to go with the second fundamental theorem of calculus. So in this case, I'm going to have negative parentheses 4x plus 1, because no matter what number I put down there at the bottom, that's going to go away anyway. It's a constant. And then I put in the other one is 4x plus 2 in parentheses plus 1. And then I simplify. So the key here is when you're working one of these questions and there's x's on both of them, you got to separate it out and work two individual second fundamental theorems of calculus. So negative 4x minus 1 plus 4x plus 8 plus 4, no, excuse me, plus 1. The 4x's are going to cancel. The 1's are going to cancel. The answer is 8. Not difficult, just a little bit longer. But it could have been a little bit more lengthy if the items that were on the integration didn't have a derivative of 1. But because they have a derivative of 1, it's quick and easy to do. What do y'all think?
doesn't seem bad.
No, not too bad.
I'm still confused.
Why?
I don't know.
Okay. Confused about this particular question or just the second fundamental theorem of calculus in general?
I mean, yeah, that in general.
Well, the whole point is to the question is it's a way of being able to change the variable to a variable we're more familiar with when you don't know one of the numbers on your integration symbol. Now, most of the time we know both of them, but sometimes we don't. And that's why knowing that you can put the x in there is kind of important, because if the derivative of it's 1, you're just putting x in. And the derivative of it's not 1, you're putting it in, and then you're putting the derivative times it. So that's what they want you to do. All right, your assignment for this is still going to be on page 283. We're going to pick up with number 34 through 42. Some of those are already bound for you and drawn out so that you can see where they start and end. And then they stop drawing the pictures and you got to bound up your own picture.
So that's when we do the whole draw it.
Uh-huh. And then the second part of this assignment, you're going to be working from 68 to 84 even. The first little part of that, you have to show both steps of the second fundamental theorem of calculus where you integrate it and then you differentiate it right back.
Short and long way, basically.
Uh-huh. The first three are the long way and the rest are all the short way.
What did you say that was?
68 through 84 even. The first three are long way and the rest are all the short way. All right. Now, that does not finish up section 4. We still have some section 4 left to do. We have got to do a little word problem and we've got to do mean value and average value. But that gets us probably at least halfway through that section. Now, the next thing that we probably should look at since we've already checked our homework is, are there any questions about 4.3 worksheet? Because I'd like to give a quiz on that, and I don't want to do that if you have some questions that you're having so much problem with.
I think just the one with the cube in it.
Just how to cube,
Basically, yes.
and that number 8?
Yeah.
8's cubing? Okay. Well, I'm going to let the video go so she can see what y'all are asking a question about then. So in question number 8 on your worksheet, can I borrow your worksheet? Okay, you're integrating -1 to 1x cubed dx. Okay. All right, so when you get started with this question, and you did 1 minus -1 over n, that came out 2 over n. Everybody agree? And when you do your capital M sub I formula where you start with the a, which is -1, plus I times 2 over n, you're saying you're having trouble when you put this in the cube on how to cube it.
But don't you multiply it by another 2 over n?
Yes, when you plug it in, you're going to say -1 plus I, which will be 2i over n, if you put that together,
Yeah.
cubed. And you're going to cube this, and then you multiply it by an extra delta x on the outside.
That's as far as it goes.
Okay. And there are 2 ways to do this. You need to decide which way is best for you, because I can't decide that for you. But you could square it first with square the first, square the last, double the middle. And then you could multiply another parentheses times that of what you've got here. That does work. Now, personally, this is just me. I can't stand that subtraction sign at the beginning. It bothers me. It may not bother you at all. But if you were going to do square the first, square the last, double the middle, and then multiply by a third one, that might be a helpful thing with negatives. It is the longer way to do it. Pascal's triangle is shorter, because Pascal's triangle says that if you can find the numbers on row 3, you can have 4 little small multiplication problems, and you don't have to do twice the multiplication. So I'm going to set that up. If you don't like that, then you can go FOIL it out by doing square the first, square the last, double the middle, and then multiply by a third one.
I want to be confusing, so like you do the first one, like you cube it out, and that would be your first parentheses.
Kind of. It's a little bit more involved than that, but yeah. Because this is 3 and 0, 2 and 1, 1 and 2, and 0 and 3. Because you want the first one to start with the highest power and work its way down, and then start on the second parentheses on the other way and work your way the other way. They all add up to 3. And then you put in your items. And this one totally drops off. and this one totally drops off, and then you just have these little small multiplying problems to work, where you like cube all this, or you square all this, multiply it by 3 and by a negative. So you're just working out power problems. Now to me, that's easier for cubing because it's just little small multiplying problems instead of having to write square the first, square the last, double the middle down, and then multiply by a binomial, which is trinomial times a binomial. But some of y'all may rather do it that way. But trinomial times a binomial with fractions could be nasty. So I think this would be quicker. But I don't know that. Some of you are really good at other things that look nasty but seem better to you. So I don't know. But that's what I would have done. And then when you get that answer, you still got to multiply by 2 over n. And then do your I work. All right. Does that get you started good enough to be able to finish that one? Okay. Does anybody else have a question about something on their worksheet? Okay. Well, I'll give y'all a few minutes to work on that then. I'm going to stop the video and let it start doing its thing so I can upload it. Because first I have to let it do its thing. And then I got to convert it. And then I got to upload it to YouTube. And then I got to find the link. And it's just a pain. I don't know why everything got so complicated. All right, Emma. You got to finish your worksheet if you didn't do this one.